optimization problems. What are optimization problems? So with an optimization problem, you're given a word problem. And when you read that word problem, there's going to be a variable that you're being asked to find the optimum value of that variable. So what does that mean? So this, we'll call it the main variable. Let's say the main variable is Q. But Q could be, this is a general variable, but Q could be the price of something, the cost of something, the time required to do something, the distance required for something. Okay? Based on the word problem, you're trying to find the optimum value of this Q. So the lowest possible cost, the lowest possible price, the shortest possible time, or the longest possible time, or the largest amount of profit. If this is profit, the shortest possible distance, right? That's what they mean by optimum value. And so the process is you read the word problem, you identify the variable that needs to be that it wants you to optimize, find the optimum value of based on some situation. Then not every time, but you might draw a diagram that shows the problem and identifies any other variables associated with the problem. So the diagram would identify Q as well as other variables that are associated with the problem. Okay, so a simple example of this is if you're going to build a rectangular, you're going to build a rectangular fenced-in area, okay, and you're trying to optimize the area. You're going to want to get the largest possible area, let's say, okay, and so you know that there's a length L or a length X and a width Y. So this is the diagram. You've got the main variable you're trying to optimize and then any other associated variables that are related to that main variable. And what you're going to then do is you're going to write the main variable. You're going to come up with some equation that relates the main variable to the input variables. So you're going to have Q as a function of X, Y, Z, etc. So for example, here, what's the area? The area is equal to X times Y. Okay, but then the next step is this is these optimization problems that we're working. This is single variable calculus. Okay, so all of these types of problems, these optimization problems in single variable calculus, are going to involve optimizing a main variable that's a function of a single variable. Okay, so we're going to learn in multivariable calculus how to do optimization problems for like a Q that's a function of more than one variable. But right now we're only going to be dealing with one input variable. So once you get this here, this Q is a function of the input variables, like A is equal to X times Y, you're always going to be able to go back to the word problem and identify there's going to be something explaining how you can relate input variables to each other. And with those equations that relate the input variables, you're going to be able to write Q as a function of just one of those variables. Let's say Y. It could be X, could be Z. Let's just say Y. So for example, here you might go back to the word problem, and the word problem says, so you've got a total of 1,200 feet of fence to work with. That's a constraint it gives you. So with that, you can now we can relate X and Y. The perimeter of this area, 2X plus 2Y, is going to be equal to 1,200. So X plus Y is equal to 600. Okay, so Y is equal to 600 minus X, and so we can substitute Y substitute the Y here, and you get A is just a function of a single input variable. You see? Now, in addition to that, though, once you get the variable to be optimized as a function of a single input variable, you're also going to want to put the correct domain. You're going to get to this function here. But then you want to put whatever the correct domain is of that input variable. This is important as well. So the domain might be all real numbers, but like, okay, for the case of fencing here, well, x can't be negative. You can't have a negative x or y, right? That doesn't make sense. So x is going to be greater than or equal to 0 and less than or equal to, well, no, it'll be greater than, yeah, something, okay. X could be 0. You could have, the area would be 0. You just have, the y would be 1200. If x is 0, y is 1200. Or you could have x be 1200, y is 0. But nothing outside of that would make any sense. So this is the domain. So we're going to have an associated domain here for y. So for example, let's say, okay, y1, y is greater than or equal to y1 and less than or equal to y2. This doesn't have to have equal in it, but this maybe it's just y is greater than y1 and then less than or equal to y2. And then also y1 and y2, that could be, you could have y1 could be negative infinity or a number. Y2 could be positive infinity or an actual number. Okay, and so once you get to this point, you've got the variable to be optimized as a function of a single input variable with the corresponding domain for that input variable. The next thing you're going to do is you're going to find the absolute maximum or minimum value of the function over this domain interval. Now, which one, absolute max or min, it just depends on the problem, the word problem, right? For the area, you're trying to find the dimensions to get the largest possible area. So you're going to find the absolute maximum value of this function over this interval. And we know how to do this, right? This is something we learned how to do up to this point in chapter 4. All right, now, but up to this point, from everything we've covered in chapter 4, there's only been, the textbook has only given us one official mathematical, stamped official math approved way of finding an absolute maximum and minimum over an interval. That was with the closed interval method. And the requirement was that, so you have an interval, but defined between two endpoints. Those endpoints aren't infinity, positive or negative infinity. It's two numbers. The function is defined at the endpoints, and it's continuous in the interval. This is the closed interval method, and the idea is you evaluate the function at the endpoints, list out those numbers. You find the critical points, all critical points within the interval, evaluate the function at those critical points, and then compare all of those numbers. The largest of all of them is the absolute max. The smallest of all of them is the absolute min. Okay? But up to this point, we haven't any deviation from this. So like if the endpoints aren't closed, one or more of the endpoints aren't closed, or maybe the endpoints are going to infinity, or maybe there's a discontinuity in the middle. We haven't talked about any official mathematical ways, math-approved ways of analyzing for absolute maxes and mins of functions that deviate from this closed interval domain here. And so a lot of the problems that we're going to work, for optimization problems we're going to work in the upcoming section, whenever you get your final function and your domain, it's going to be a closed interval, right? This is a closed interval. If y1 is a certain number and y2 is a specific number, it's y is greater than or equal to on both sides. So it's closed. So it's a closed circle here. So that's a closed interval. You use the closed interval method, get the absolute max or min, and you've solved the optimization problem. But what I'm trying to do is I want to give you the tools to be able to analyze any scenario that you come across, because real life is general. Real life, you can come across, anything can happen, right? And so, well, the first thing is that there was a video a few videos ago. The video was titled General Absolute Maxes and Mins. I'll post a link to that video in the description, but what I talk about in that video is if you have any situations that deviate from this closed endpoints continuous function, how could you analyze those for absolute maxes and mins? If you had a discontinuity, if one of the endpoints is open, right? So you take the limit as x approaches the endpoint from the left, right? I talk about ways to analyze all types of functions for absolute maxes and mins. And so if you make sure you watch that video, and so that will give you more versatility for if whenever you're solving an optimization problem, you get your final function and you get any kind of domain, not just one with a closed interval. Okay, but before we get into the optimization problem section, I want to mention a few more things that might potentially confuse you when you're analyzing for the absolute maxes and mins. So, okay, first of all, so y1 could be a single number, y2 could be a single number, but in general, y1 could be like negative infinity, y2 could be positive infinity. But then also you could have, like we saw in the curve sketching videos, and I made a whole separate video about this before the curve sketching videos, but you could have domains with endpoints with more than 2 endpoints. So like, here's a domain. Okay, so the domain here is all real numbers, except for there's anything from -1 to 1, not including -1 and 1, is not part of the domain. Okay, and as I talked about in those other videos, -1 and 1 are considered endpoints here. Okay, if this is confusing to you, go watch the video. It was titled Critical Points versus Endpoints, and you'll see why -1 and 1 are considered endpoints here. And so really the idea is, in general, what you're going to do is you're going to identify what the domain is. You're going to see what are the endpoints. Then you're going to look at the endpoint behavior. You're going to take the limit as x approaches all of the endpoints. So you'll do this for any domain. So you could have a domain if it's just negative infinity to infinity. Then there's just these 2 endpoints here. Okay. So, but let's look at this domain. You'll take the limit as x approaches negative infinity of the function, the limit as x approaches positive infinity. Then you'll take the limit as x approaches -1 from the left, and also the limit as x approaches 1 from the right. And then you'll note whatever those limits are, you'll put those values off to the side. Okay, you'll list out what those values are, and you'll save that for later. Okay, then the next thing you're going to do is you're going to then find the critical points with respect to the first derivative. And again, if you're wondering, well, what's the difference between a critical point and an endpoint, go watch the video. I'll post a link to that in the description as well. Critical points versus endpoints. I go into detail on exactly what I mean by that. But we're just analyzing a domain for the absolute max and min of the function. You look at the endpoint behavior, put that off to the side, what those limits are. Then you find the critical numbers with respect to the first derivative. That's one thing to note, is that, so you got any function, if this is going off to infinity. When it comes to analyzing for maxes and mins, local maxes and mins, but even just we're talking about absolute maxes and mins over an interval. The only relevant critical points are with respect to the first derivative. The critical points with respect to the second derivative don't matter. Okay, so you're going to get all the critical points with respect to the first derivative. Then you're just going to analyze it. Is it a vertical asymptote? Is it a local min, local max? What is it? And really the idea is if the function exists at the critical point, find what the function is equal to at that point and note that off to the side. If it doesn't exist at the critical point, then take the limit as x approaches that critical point from the left and the right and put that, whatever that limit is, off to the side. Then once you have the endpoint behavior and all of the critical point relative to the first derivative behavior, you're going to compare all that and find, okay, what's the absolute max and min? Now you might be saying, well, wait a minute. How can we know that if all we're analyzing is the endpoint behavior and the critical point with respect to the first derivative behavior, how do we know that that's all the information we need to determine the absolute max and min? All right, well, think about this. Let me give you an example. So let's say we have a function that's the domain is 0 to infinity. All right, you take the limit as x approaches 0 from the right. Let's say that goes to infinity. All right, now you take the limit as x approaches infinity of the function. Let's say that also goes to infinity. All right. Now, then you look for critical points. Let's say there's only one critical point. Right here. Okay. You determine that's a local min. And so now you look and you see, okay, I've got my endpoint behavior. X is going to infinity at both of the endpoints. I have a local min, and that's the only critical point with respect to the first derivative, is that local min. Well, this is not an official math. I'm not giving official math statements here, but you can use logic and realize that that's going to be the local, the global min. You could safely say, in my opinion, as an engineer and with my experience, you could safely say that's the global min. This critical point is the global min. Why? Again, I'm not proving this. I'm not giving you a full math proof here. But the reason is because there's no other critical points. There's no way, if you know you're going off to infinity as x goes to the right, all the way to as x goes to infinity, the function is going to infinity. And as x goes to all the way to the left endpoint, the function goes to infinity. You can't, without another critical point with respect to the first derivative, you can't, how could you possibly get below this value? Think about it, okay? So you might say, all right, well, there could be a discontinuity. You know, as x goes to infinity, the function goes to infinity. This is a critical point. You would find there'd be a critical point here and here. You would analyze this as you would take the limit as x approaches this from the left and from the right. That would be two different values. So you would figure out that it's a jump discontinuity. But you would find this as a critical point. Okay, what if you did this? What if there was no discontinuities? Okay, as x goes to infinity, this goes to infinity. The function goes to infinity, but no, you would find a critical point here and here. Okay, you might say, all right, well, what about if there was a bunch of inflection points? So there's a bunch of, as x goes to infinity, there's a bunch of critical points with respect to the second derivative. Okay, so we're concave up, we switch to concave down, switch to concave up, switch to concave down, but there's no horizontal slopes. There's no critical points with respect to the first derivative. You can't there's no way for you to come back below this point. You see, so the main point I'm trying to make here is that watch the video where I talk about analyzing for general absolute maxes and mins. I'll post that in the description. Watch the video. Also watch the video on the difference between critical points and endpoints. I'll post that in the description as well. With that, all you need to do is analyze the endpoint behavior and then also analyze the critical points with respect to the first derivative. With that, all you need to do, once you get to this point in an optimization problem where you've got the variable to be optimized as a function of a single variable and the corresponding domain of that input variable, and you're trying to find the absolute max and min or min over that interval, over that domain, no matter what the domain is, all you're going to need to do is analyze the endpoint behavior, take limits as x approaches the endpoints of the domain, and then analyze the critical points with respect to the first derivative. Then that's all the information you need to figure out what the absolute max and min are. Okay, so with that, let's now get into the optimization problem section.